Welcome to the Crazy Hat Chemist. So another video in bonding and molecular structure. So let's get moving. Bam! So today we're going to be talking about water's molecular geometry and oh so more, baby. So first you need to know the formula for water, HOH or H2O. Everybody knows that, hopefully. So we're going to look at our periodic table and figure out the number of valence electrons. For hydrogen it's 1, but there are, and then oxygen is 6, but there are 2 hydrogens. We're going to sum these two numbers up and we're going to get a total of 8 valence electrons. Then we're going to divide that by 2. Then we're going to get pairs of electrons. So we have 4 pairs of electrons. From this information, now we're going to put the least electronegative element in the middle, but never hydrogen. Therefore, by default, even though oxygen is the second most electronegative element there is, it's going to go right there in the middle. Okay, but it's never hydrogen. Okay, then the hydrogens go outside in the X marks the spot pattern. You could have had them up and down. Or you could have had one right, one left, one at the left-hand side, one below, one on the right-hand side, one above. It doesn't really matter. Okay, now you're going to place those 4 pairs of electrons around this in the appropriate way for the Lewis dot structure rule. So the first rule is to place bonding pairs of electrons between the central element and the outside element. Okay, now I'm going to verify the duet rule. The duet rule is for hydrogen. Therefore, I cannot do the next rule for the Lewis dot structure rules and place lone pairs of electrons on the outside elements because the duet rule has already been satisfied for hydrogen. Therefore, the next set of lone pairs of electrons, which are going to be 2 of them, are going to go on that central oxygen because it's deficient in an octet, and oxygen is one of period 2 elements, one of 4 period 2 elements, which must have an octet. So I'm going to place those 2 lone pairs, 2 lone sets of electron pairs on the central element of oxygen, and now the octet rule is verified. Now I'm going to clean up this Lewis dot structure and make it look really nice and pretty. That is, bonding pairs of electrons are lines, non-bonding pairs of electrons are still dots. And then this is what I get for my Lewis dot structure. Okay, now I'm going to look at my axe and figure out what is the axe shape. So the A is the central element, that's the oxygen. The X's are 2 hydrogens, so that's AX2. And then there's 2 sets of lone pairs of electrons on the central element, and that is E2. So you should have AX2E2. So how many bonding do you have? 2 bonding domains. How many non-bonding domains do you have? 2 non-bonding domains. So that's 2 bonding, 2 non-bonding domains. From that, you should be able to get the shape. That shape name is either bent or angular. You can write bent, you can write angular. You don't need both. That's just fine. Okay, now we're going to get the bond angle from this. It is much less than 109.5 because it's a tetrahedral arrangement of electron domains around the central element, but 2 of the domains are bonding, 2 of them are non-bonding. Okay, just like the previous one of NH3 ammonia that we had, there was a compression of bond angles, and that's due to the lone pairs of electrons on the central element. And there is a further compression of bond angles, and that's why the bond angle here for water is 104.5, or I rounded it to a whole number there for you at 105. Okay, now we're going to do the hybridization of this, and we're going to count S, P1, P2, P3. It's sp3 hybridized. Okay, now what we're going to do is going to get the polarity of this. And so I have this as a model here for you. So I've shown this to you before, but here is the model for water. The red thing in the middle, that is the oxygen. I'm holding on to the 2 lone pairs of electrons. Looks like Mickey Mouse. The 2 white ones are the hydrogens and the grays are the bonding domains. Okay, so is this symmetrical or asymmetrical? The question is, well, I'm holding on to one side. The other side over here is asymmetrical, so that would be polar. Water is most certainly polar. Okay, wait, we are not done. We got more stuff. Besides the crazy hat, we still got more stuff dealing with water. Okay, so check this out here with water. So the consequences of this polarity with water is dealing with a microwave oven. Okay, so microwaves cause polar molecules to vibrate. Okay, and that is the molecules themselves. This bond vibrates. It goes back and forth, back and forth. The rotation of the bond is there as well. And also the molecule flips back and forth like this. Boom, 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 really fast. I mean, we're talking 2.45 billion times a second. Okay, this increases the kinetic or thermal energy, and that heats up food. So that means that the more liquid in your food, the more water in your food, the faster it heats up, and the more consistently it heats up in that microwave. Microwaves has relatively long wavelengths at 12.2 centimeters. Therefore, they have relatively low energy, low frequency, and not enough energy to break this bond. Okay, it's not enough energy to break chemical bonds right here, yet it's enough energy to vibrate this polar molecule. If water were not polar, then it wouldn't vibrate. So if we were drinking like methane liquid or something like that, which is non-polar, then this wouldn't work at all, and microwaves would be completely useless to us for heating up food. Okay, I got a great crazy hat here for you, so hang on to that. Okay, bam, I like it. Give me a thumbs up if you like that video. Give me a thumbs up if you like the hat. Subscribe to my YouTube channel. Pass on the word that this is the place where you get all your chemistry questions answered. The best lecture series there is by far by none. I'll see you next time for more cool chemistry problems. See you then. Bye now.